Today we're going to start our final topic before the summer holidays, which is the normal distribution. This will actually span across the summer holidays, so we'll do most of it before the summer and then we'll do a little bit of it once we get back, or hopefully get back in September. Hopefully we'll be able to do that face to face. So the normal distribution is a way of modelling continuous random variables. The only distribution we've looked at so far was the probability distribution for a binomial random variable. So that was for discrete data. Remember, it represented the number of successes out of n trials. So for example, the number of times that you get ahead when you flip a coin 30 times. And our random variables would be 0, 1, 2, 3, 4, all the way up to 30. It would be all the possible values, and we could find the probabilities of those. That was discrete data because we could list those individual number of successes. With the normal distribution, we're going to be looking at continuous data, so for things like height and time, where you can't measure them absolutely accurately, we cannot get them exact, and there is an infinite list of possible outcomes, so we can't write down the list of possible measurements. Because of that, if we want the probability of any particular value, we would assign that a probability of 0. So if we were looking at the heights of students, we would say the probability of a student having a height of 165 centimetres is 0, because it's so unlikely to be exactly that measurement. Now, when it comes to continuous data, we've looked at drawing histograms, and we've ended up with histograms of all different shapes and sizes, but we mainly get 3 different distributions when we plot a histogram. We get one with positive skew, where the bars to the left are taller and it tails off towards the right. We get a symmetrical distribution, like this one here, or we get one where there's a tail to the left and the bars to the right are taller. These represent positive skew, symmetrical distribution and negative skew. And if we made those bars really narrow and we joined up the middle of the tops of the bars, we would get these curves here. So we use these curves to show positive skew, negative skew and a symmetrical distribution. And the symmetrical distribution is a normal distribution, so that's what we're looking at today. Just to put some facts in about this skew, if you've got a symmetrical distribution, your mode, your median and the mean are all the same. We know the median's in the middle, the mode is the most common, and the mean, if we add them all up and divide by how many there are, the big values and the small values will give you a balance, so your mean is in the middle. However, if you have a positive skew, your mode is still going to be at the peak, but your median, because there are more values to the right, your median will be to the right of the mode. It will be higher than the mode. Your mean will be skewed by the extreme values right towards the end of the tail, so your mean will be even bigger than the median, further to the right than the median. For negative skew, we get the opposite happening. So the mode is still at the peak. The median will be to the left of it, so the median will be smaller than the mode because you've got more values to the left, so your middle value is going to be further to the left. And your mean will be affected by the extreme values towards the end of the tail, so your mean will be even smaller than the median. So there's a little point to make at the bottom of the sheet here, which we know. If we've got extreme values, then the median is a better average to use than the mean. We've been talking about that for a long time. So let's focus in on the normal distribution. We call this curve that we get a bell-shaped curve because it's symmetrical like a bell, and we call the mean mu. Remember, the mean will be the same as the median and the mode. We call the standard deviation sigma, and I've marked in here sigma to the right of the mean and sigma to the left of the mean. Now, within one standard deviation of the mean, you get 68% of your values. So under a normal distribution, 68% of the data will lie within one standard deviation of the mean. If we look within 2 standard deviations of the mean, so either 2 standard deviations less or 2 standard deviations more than the mean, you will get 95% of your data. So 95% of the values will be within 2 standard deviations of the mean. And if we go to 3 standard deviations from the mean, so we're looking at all of this, that will be 99.8% of the data. So that's only 0.2% of the recorded data would be beyond that. We don't state a maximum or a minimum value, but if you go to 5 standard deviations away, 7 standard deviations away, there's going to be an extremely low proportion of data values within those ranges or outside of those ranges. So we talked about an example of the normal distribution being heights, but also weights tend to be normally distributed. So let's say we have recorded the weights of a large number of students. We found the mean weight to be 46 kilograms, so that would be our mu is 46, and the standard deviation is 3 kilograms, so we would say sigma equals 3. We would write this, if it's a normal distribution, if we had x is the random variable representing the weights of the students, and we're saying that those weights are normally distributed, we can write it as x is distributed as a normal 46, and then we would put 9. So we use mu as this value here, and we use sigma squared as this value here because we use the variance as opposed to the standard deviation. So remember from earlier in the course, variance is the standard deviation squared. We tend to use standard deviation normally because standard deviation uses the same units, as we can see here, the same units as the data. But when we're using the normal distribution notation, we put variance in, which is, to be frank, a little bit irritating. So if we know that our mean is 46, then half of our pupils will weigh less than 46 and half will weigh more than 46 because of the symmetry. And we know if we add 1 standard deviation, so we add 3 to our mean and we take 3 away from our mean, we know that 68% of our pupils will weigh between 43 and 49 kilograms, and they will be evenly distributed to the left and the right of the mean. So we'll have 34% of pupils between 43 and 46 kilograms and 34% of pupils between 48 and 49 kilograms. We then know that 95% lie within 2 standard deviations of the mean, so within the range 40 to 42, we will have 95% of our pupils. 47.5% will be between 40 and the mean, and 47.5% will be between the mean and 52. So that we just get those values there from adding and taking away 2 lots of our standard deviation from the mean. So if we've got 95% within the 40 and 42, that means we've got 5% outside of that range. So that means we've got 2.5% here and 2.5% here. So 2.5% of pupils weigh less than the 40 kilograms and 2.5% weigh more than the 52 kilograms. and only one student in 1,000, so that's, remember 1% would be 1 in 100, so 1 in 1,000 is 0.1%. So we're now looking at being 3 standard deviations from the mean. So 3 standard deviations from the mean, 3 standard deviations is 9. So 9 away from 46 would be 37 kilograms, and only 1 in 1,000 would be beyond 3 standard deviations to the right of the mean. So 46 plus 9 would be 57 kilograms. It wouldn't. It would be 55 kilograms. Okay, so that's our introduction to the normal distribution. I'm going to upload the exercise on this to show my homework. I don't really expect you to have to do this, but you can do it if you want, and I'll put the answers on there as well. It shouldn't take you too long if you want to do it, to make sure that you've fully understood that introduction. But what I want to look at is finding probabilities with this normal distribution using our calculator. Now, we've already covered a lot of the information at the top of the sheet. So we've talked about mu being the mean and sigma squared being the variance, sigma being the standard deviation. We've talked about the symmetry. We've talked about the bell-shaped curve. We didn't use the word asymptotes, but I said to you that we don't say there's a point where we get our maximum possible value and our minimum possible value. So those curves will tend towards a frequency of 0. But won't actually meet the x-axis. Because we use our curve to represent probabilities, and probabilities add up to 1, we say the total area under the curve is equal to 1, and there are points of inflection at mu plus sigma and mu minus sigma. That's not an essential piece of information. So our normal distribution can have any mean and any standard deviation, but there is a standard normal distribution which has a mean of 0 and a standard deviation of 1. We call that distribution of variables that can be modelled using that distribution Z, and our notation is Z is distributed as normal, 0 for our mean, 1 for our variance. We'll look at that in more detail, but we've already said that if we've got a different mu or sigma, we would use this notation here. So example 1 uses the standard normal distribution. So our mean is 0 and our variance is 1, which means our standard deviation is the square root of 1, so also 1. So mu is 0, sigma is 1. And we want the probability that Z is less than 0.06. So on our calculators, we need to go into the distribution setting, which is option 7. You can see the bell-shaped curve drawn as that option. And we're looking for the cumulative distribution function. This is because we're looking for Z being less than 0.06, not equal to a value. Remember, we said that we can't have it equal to a value. So less than 0.06, so cumulative distribution function. And our lower value, well, we said that we don't have a lower value for our normal distribution. We said there isn't a minimum possible value. So I'm just going to put in a really tiny number, one that's at least 4 standard deviations from the mean, because below 4 standard deviations from the mean, we've got a really, really low probability of anything happening. So what a probability which goes into such low decimal places that it's not going to affect the answer that I write down. It's going to be beyond my rounding. So like I say, we could go for something that's 4 standard deviations below the mean, or we could just go for a really, really small number, like -9 times 10 to the power of 99. That's a really, really small number. My upper number, I'm going to use 0.06. So I am looking at the probability that z is less than 0.06. If I draw a quick and not very accurate bell-shaped curve, we know the mean is 1, so that's the middle. 0.06 is down this end somewhere. So I'm looking for between, well, technically minus infinity, we'll just go for a really, really small number, and 0.06. And the area represents the probability. So my upper value is 0.06. My standard deviation is 1. And if I go back in, I need to check that my mu is 0, and hitting enter gives me that probability. And we're going to jot that down. Let's go for 4 decimal places. Now, if we want the probability that z is less than or equal to 0.06, remember for these continuous random variables, we give the probability of it being equal to 0.06 as 0, because there are infinite possibilities. So they are distributed so finely that the probability of z being actually equal to 0.06 is 0. So this is the same as the probability that z is less than 0.06, which we've just worked out. Okay, so that's the probability z is less than or equal to 0.06. If we want the probability z is less than 1.89, let's go back in. And we're going to still keep our lower value very, very tiny. Our upper value this time is 1.89. We've still got a standard deviation of 1 and a mu of 0. So we get 0.9706. And we would expect this time a big probability because, sorry, our mean is 0, isn't it? Because 1.89 is up here. It's nearly 2 standard deviations from the mean. So we're going to expect a large proportion of our curve to be to the left of that. And then if we look at the last one, our upper value this time is 2.3567, and I'm going to expect a really large probability now because that's a long way to the right, and I get 0.9908. So that was the standard normal distribution, and all of those we were looking for the probability of our standard normal variable being less than a value. But now let's have a look at a different distribution. This time our mean is 30 and our standard deviation is 4. So my curve is going to be the same shape, but it's going to be symmetrical about the mean, which is now 30. So if we want the probability x is greater than 24, 24 will be below 30, so we're looking for a probability of over a half. Half would be greater than 30, so greater than 24 is over a half. When we type this in, this time our lower value is 24 and our upper value is tending to infinity, so just type something massive in. So you could go for something that is more than 4 standard deviations from 30, so 16, something that's bigger than 46. Let's just get into the habit of going for something just massive, so 9 times 10 to the 99. I need to go back because this time my sigma is 4 and my mu is 30. So my probability, like we said, we were expecting something greater than 0.5 and we get 0.9332. This time we want the probability x is greater than or equal to 24. Remember, the probability of it actually being equal to 24 is 0. So this is the same as the probability x is greater than 24. So 0.9332 still. Then we want the probability x is greater than 17, so we're just going to change that lower value, keep the upper value as being massive, and we've still got the same standard deviation and mu. So we get 0.9994. We would, if we were looking at 17, be expecting a probability that's even bigger than the one before. And then if we want the probability x is greater than 19, we're looking for something between those two. So let's just put our lower value as 19, keep everything else the same, get 0.9970, which is in between those previous two answers as we expected. Okay, example 3, we've got the same distribution. It's asking us to draw a diagram to make sure our answers make sense. So let's draw a quick diagram. Doesn't need to be anything flash. So our mean is 30. And this time we're looking for between 32 and 40. So lower 32, upper 40. These are actually easier to understand because you don't need to think of a massive or a tiny value to put in. And we get 0.3023. So we were expecting something for 32 to 40 within this 0.5, so something less than 0.5, so that seems a reasonable value. For 33.5 to 38.2, we'll expect a smaller probability. Let's check we get one. 33.5 to 38.2 is 0.1706. And then if we want x is less than 27 or x is greater than 32, so that would be x is up here or x is down here, we can work out those two separate probabilities and add them together, or we can do 1 minus the bit that we don't want. So the probability that x is greater than or equal to 27 but less than or equal to 32. And that would save me having to do two things on my calculator. So I'd do 1 minus the number that I get with a lower of 27 and an upper of 32. And we get 0.5352. And we can do the same for this one here as well. And this time we will expect a smaller probability for this bit because we're looking at a tighter range. So we're looking at 1 minus 0.2150. So we get a bigger answer. Of 0.7850. Okay, the final example, an IQ test is applied to a population of adults and we're saying that the scores are found to be normally distributed. We're calling the scores X and they have the normal distribution 100, 225. So that means that our mu is 100 and our sigma squared is 225. So sigma is 15. Adults scoring more than 140 on the test are classified as genius. So we're going to find the probability that an adult achieves a genius classification. So that's the probability that X is greater than 140. So we've got an average of 100. So 140 will be here. So on my calculator, I want a lower value of 140 and an upper value of something massive. This time standard deviation 15 and mean 100. So the probability is 3.83 times 10 to the minus 3, so 0.0038. 8 to 4 decimal places. Oh, but we want 3 significant figures, so we need another figure on there. And then 20 adults take the test. We want the probability that 2 or more are classified as genius. So we're now looking if we have a new random variable, and that's the number of geniuses. We'll go for genii. Let y be the number of genii, then y is a binomial distribution. It's binomially distributed. We're doing 20 trials and our probability of success is 0.00380. We want the probability y is greater than or equal to 2, which is 1 minus the probability x is less than 1. Remember, x is less than or equal to 1. Remember, on our calculator, if we use the binomial cumulative distribution, that will give us the probability x is less than or equal to a value. So x is 1, n is the number of trials, so that's 20, p is our probability, which is our previous answer, and we get the probability of 0.9973. So when we subtract that from 1, we get a probability of 0.0027 of having 2 or more genii in our trial of 20 adults.